So this whole business with currying and partial application looks even more interesting when you apply it to operators, right? Like you have operator plus or multiplication. Operator plus, if you put it in parentheses, it becomes a regular function, right? Normally it's an infix operator, so it takes two arguments, one on the left, one on the right. But if you put it in parentheses, it takes two arguments in front of it. So the signature of plus, let's just simplify it and say it's double. And I'm going to even write the D instead of double because
you're lazy.
Patience, yeah. So it's double to double to double, right? So two arguments that are double, one on the left, one on the right usually, right? And this is the result. It's also double. I mean, the real signature involves num and stuff like this, but this is good enough for us. Okay? So we can define a function by partially applying plus. Let's call it inc for increment, right? Well, this is not even a function because it takes no argument. No, sorry. takes an argument. And okay, so normally I would write it x plus 1. Right? Or 1 plus x, or whatever. Let's write it 1 plus x. But I can also say that inc is a partial application of the operator plus to 1, right? Now this can be rewritten as plus in parens acting on 1 and x. The space is here, right? Well, this space is not really necessary, but this one is. So it's a function called plus applied to 1 and x, right? So partial. So the point-free way of writing things is when we remove the point, right? And it often looks just sort of like canceling the right, the stuff on the right. You know? Because they are both on the far right. The x is here on the far right and x is here on the far right. You can just cancel it and say x is plus 1. So I don't know if I need parent. Probably I don't even need parent. Do I? Probably do. Okay. So this means that the operator plus is applied to one argument. So these are the sections, and it's part of the partial application and curry. Now, a completely different thing. Okay, we talked about functions, and there's much more about functions. But for now, let's just stop there and talk about data structures. And again, you have to like unlearn everything you've learned about data structures in other languages. It was all wrong. So data structures in Haskell, they start very simple because there is theory behind them. So we start by asking ourselves the question, because data structures form types, right? Every data structure is a type. What are types? So we have to go back to semantics of Haskell, right? Semantics of Haskell is math. So to first approximation, like the simplest approximation, we can say a type is just a set of values, right? It's not exactly true, but I mean, I would like to go into category theory with this, but
are types values?
Now we have a problem.
In the category of types.
yeah. Russell's paradox. Okay.
So if you were to describe it in terms of category theory, how would you describe it?
I'm not gonna say that.
Refuses to control.
He's biting me.
No. Aside from the
Baiting.
paradox issues, what?
All the paradox issues. No. I'm not gonna say that.
One thing you can do is define universe of type. So you have type and type 0 and type 1.
Yeah.
That's just like the ramified field of type. And type 0 cannot reference type 1 or type 0. So you don't have Russell paradox.
Yeah? Okay. So you have universes, right? So you have one universe of data types, and if you want to say, now I'm talking about this universe, is this a member of this universe? Is this universe a member of itself? No, it's not. It's a member of the next universe and the next universe and so on. So we have these infinitely many universes, right? More or less. Yeah. Okay. So there is, in mathematics, there is set theory. Set theory is very simple. It abstracts everything from a set and just says, set is a bunch of elements, and is this element a member of the set or not? And so on. So very simple reasoning about sets. And we can use the same reasoning for types. And we can say, okay, so like, a type integer, what's that? And it's a set of integers, right? Okay, it's infinite. It's an infinite set of integers. We probably can't represent all of them, but mathematically, that's what it is, right? Or we can have set of ints. That's a different type in Haskell, which is 32-bit integer. So that corresponds to a set modulo 4 billion or something. Right? Integers modulo 4 billion. If it's unsigned, it's signed. Okay. Let's not get into the details. A Boolean, for instance, that's a very nice, simple example. It just has two elements, true and false. So it's a two-element set. Okay. We also have sets that have like the basic sets from which everything else can be built. It is an empty set. That's part of the set theory. An empty set, and there is a singleton set, which is also very important. So what are the types corresponding to these weird sets, like an empty set? Okay, so in Haskell we do have something that's representing an empty set. It's called void. But it's a very weird type. Why is it so weird? Because it has no elements. So there is no way of constructing an element of void. There is no constructor for it. It's a type that can be only used as a type. You can never use a value of this type. But you can do weird things with it, like say, can I have a function from void to void?
The identity function.
Exactly. Yes. So identity function is so general that it even works with void, with an empty set. What it does, it says, hey, if you give me an element of void, then I can sure return it to you. Of course, you can never give me an element of void because one does not exist, because it has no elements. But, for a mathematician, this is like in vacuum. It's true in vacuum. Great. This is why you don't have to have all these special cases. So what do I do with one element set, two elements set, 0 element set? Who cares? This formula works for everything. Okay? Now there is a little bit of cheating in this, and probably if somebody's watching this video, they might say, this is all wrong. Of course, every type in Haskell has this bottom, right? This thing, this element called bottom. And that corresponds to a calculation that never ends, like an infinite recursion or infinite loop, right? And that's fine, okay? And in most cases, it really doesn't matter that much. So there is really no empty set in Haskell because of this bottom thing, because Haskell is lazy. Okay? The bottom thing is just because of laziness of Haskell. So there are some complications with the type system in Haskell. ML, for instance, doesn't have this problem because it's not lazy. Okay? And there are people who will say Haskell is really awful language because of this stuff.
What's the type of functions that never return in ML?
Bottom.
I thought there was no bottom.
No. What is the function?
Well,
Just give
we
it
did.
an-
We had one.
No, he's talking about ML.
Oh, ML. I'm sorry.
Yeah, I don't know.
You just give it a type of variable as because if there's a lazy, there's a bottom type, because it can return anything.
They can return anything, right?
So just give it a free variable.
It's just the thing is that when you call this function, it will never return. Whereas in Haskell, this function actually returns because it's lazy. It will never go into this infinite loop. So it returns something that signifies I will go forever.
But bottom is a value.
It's a value, right? What did I say? No, the type is whatever. The type is generic type. Right?
So bottom
Any
is a
type.
member of every type.
Bottom is a member of every type, including void. Okay. But these are the things that scare people. That scare people from Haskell, you know, and then it's really not necessary. So if you just believe me in faith that void has no elements, then you're fine. I can do some hand waving.
Do bottom live in?
And now you're
box?
pushing me on the bottom.
No, I mean, do you have bottom in a box type, like a box integer? You have bottom in it.
It's like throw a single argument exception.
I mean, in a box
I don't
type.
think it helps to obsess about bottom right now.
Okay.
Yeah. I know. He's interested.
We can talk about it when we have beer.
Let's
Bottoms
be
up.
engineers about it.
Okay, so void, kind of weird type. But singleton is extremely important. And the singleton set, the set that has just one element, which is totally like meaningless element, just the element, right? It's the type is called unit, but it's actually denoted by open close paren. So that's the notation for it.
Do we think of this as a tuple that has 0 elements in it?
Yeah, nullary tuple. Yeah, there's no elements. Yeah, so like if you want to have a sequence of these things, you know, you have a pair, you have a triple, quadruple, and so on. This is actually in category theory. This really makes sense to have these higher order because these are called products. I'll talk about products anyway. So, I talked to some people who are really experts in C++, you know, and I asked them, so what is the type void in C++, right? And they say it's a type that has no elements, just like this. That's not true. Void in C++ is actually a unit. It has one element, which is just like a token. You know, it's a token. When a function returns void in C++, it really returns a token which you can pass to another function that also expects unit, also expects one element. But this element is only one, and it's available everywhere. You can just get it from the air. You know, unit. Here it is. Okay, so Yeah, this is especially important because, like, when you do composition of functions, right? Try to write composition of functions, a composition operator or just function compose in C++. You'll write your function beautifully, and then somebody comes, oh, what about a function that returns void? And can you compose it with a function that takes a void?
That's my
Right. Okay, so I have to write a separate template for that in C++. Whereas in Haskell, well, you just have a function that returns. There aren't that many functions that produce or accept unit because we are dealing with pure functions. So now let's talk about, so how would we declare this type, right? So it is actually built into Haskell, but it doesn't have to, it's just syntactic sugar for something that's a data declaration. When you create a new type, you can declare a type by saying data. Okay, that's the keyword data. And now, let's say I want to define the type unit. So I'm not defining the built-in unit, I'm just defining my own type of unit, okay? So I'm defining a unit, and the definition of a data type is very similar to the definition of a function, except that it has data in front of it. So you just say unit equals, again, equal sign, like in the definition of function. And now you have to say, so this is type, and now you have to say, how do I construct a unit? Okay, so here's a type, and here's the constructor for this. So how do you construct? Well, we can call it, the constructor, we can call it U. Okay? So if you want to construct a unit element, you will use this. And if you want to use operators instead of, so this is not true, right? This is just this one. So you would say data, and instead of unit, you write the parentheses, you write the operator that signifies type. Just like you can use operators as functions, you can use operator for names of data types, okay? And the constructor is called the same thing, okay? And this is something you have to get used to in Haskell, that very often, because these are completely separate namespaces for types and constructors, data constructors, that you can use the same name as type as data constructor. And this is kind of important in Haskell, that you don't multiply names, that you have this Occam razor. Why create new entity if you can reuse the same name? Because the compiler always knows whether you are talking about type or a type constructor. Right? So you use the same name because otherwise you pollute the namespace. The namespace in Haskell is kind of pretty open. Like if you have one data type that has a particular name for a constructor, then in the same file you cannot use it for another data type that has the same name for a constructor. And this is gonna change in Haskell. Right?
Okay. So those of us who are into object-oriented languages probably think of constructors as a special kind of function. Is this a special kind of function?
It is.
Okay.
However, in this case, it's special. Right, because like it has no arguments, and the constructor takes no arguments, so it's like a very, very borderline case. But I will show you things that actually have interesting things. Okay, so I just mentioned this in the beginning to show you what the most basic sets in set theory correspond to in type theory. Yes?
Can you just say one word about where the name data comes from? Why is that chosen?
Because it's a data type, I guess.
Okay.
Well, okay,
I mean,
so
why do they call it
so
type?
there are two keywords used in Haskell. There is data and there is type also. Type is used for type synonyms. Data is used to create new types, right? Define new types. And there is yet another you can call new type, which is kind of in between these two. Okay, so starting with these two basic types, you know, we can sort of bootstrap ourselves into creating more interesting types. So suppose that we have two types or two sets. If we want to be on the mathematical side, we have two sets. What can we do with two sets? How can we create a new set out of two sets? The simplest thing is to take a product of these two sets. Cartesian product,
Yeah.
right? That's pairs, okay? So a product of two sets is a set of pairs where the first element is from one set, the second element is from the second set. That's called a Cartesian product. Right? Can we define Cartesian product of types, since types are sets? Well, of course. So we start with the keyword data, right? And now we are defining a type. Let's call this product. Okay, but product of what? It has to be a product of two types, right? So let's put two type variables here, A and B. Because you can take a product of any types, arbitrary types. So you can as well put a type variable here and say, I'm defining the most general product of any two types. Okay? Now this thing now is called the type constructor. And it's just like a function, right? You said it, but it has a capital letter here. But it's a function on types. It takes two arguments, which are types, and produces a new type called product of A and B. Okay? So think of this as analogous to function. This is what I was talking in the first lecture, right? That you have this hand sticking out. Like the syntax for data types mimics the syntax for functions, except that these are now functions on types. And in fact, in the future, Haskell is like going to really collapse types and values and kinds and so on into one big universe.
Is there no equals after the B here?
Well, that's the next thing, right?
Oh.
So this is just the function product takes two arguments and it equals just like in definition of a function, right? So now on the right hand side of data declaration is a constructor. So how do we construct a pair? Well, we call this constructor P, although as I said, these are separate namespaces, so I could call it product if I wanted. Okay, but just for simplicity, I'll call it P.
No, for simplicity, call it product, so we're not confused.
No, because I think it's more confusing if they are the same. You know, because then you don't know, am I using a type constructor or am I using a data constructor?
That's the explicit stuff.
So to start, let's do the explicit stuff, okay? So this is called data constructor. And in order to construct a pair, I need two arguments, two values. One value of type A, this one, and one value of type B. Okay? So, are you writing it? Oh, okay, great. So in the interactive environment, you can actually ask the compiler, what is the type of P? What is the type of this guy P? What is it?
It's
Okay.
A.
So it takes A, B, and it produces product of A, B.
And the fact that we
No
use product and P, yes, no
okay.
parentheses.
Yeah,
The
okay.
reason that using product and P explicitly making a distinction is helpful here. You see product P appears here, not P.
Yeah, so this is product, this is a type constructor, okay? So this is a type. Product AB is a type. Yes?
So in the definition of topic, we could write P, X, Y, because it's a simple namespace.
Here?
Yes.
No, because A is the same as this.
Those
Okay.
are types.
So what this is a type signature for the constructor of product. P is a function that takes type A and type B. Yeah.
So the right-hand side is also type definition.
Well, you see, it has a capital letters, which means it's related to types, right? And this kind of is a simplified signature of the type of the data constructor. And data constructor P is a function. In this case, it's a function of two arguments. The first argument is type A, second argument is type B, and what it produces is produces an element of a product of AB. So now we are back to an actual function. Every constructor is a function. It's a kind of special function, but it's a function, right? And you can use it as a function. You can call it with two arguments, and you'll get a value which is a pair. Okay.
What are some instances where you would use the type constructor rather than data constructor?
Well, the type constructor you use in type calculations. When you are specifying a type signature of something, you will use a type constructor to, yeah. Now, the type constructor, okay, we'll get to this actually, what the type constructor does.
So Bart, before you go on, can you just explain what the capitals and why are some capitalized and some lowercase?
So this is capitalized definitely because it's a type. Types are capitalized.
A and B are type variables.
These are type variables, and they can be they are lowercase always. Type variables. Type variables are lowercase, and there is no confusion because type variables always occur in the context where you are creating a type when you have a type constructor.
And then the type constructor on the right-hand side is
Data
also
Data constructor.
Sorry,
Mhm.
thank you.
I confuse them sometimes too.
That is capitalized.
That's capitalized even though it is a function.
Function.
Yeah. Now, why is this capitalized?
Because it's just like C++.
It's just like C++.
It doesn't even have to be. I mean, you can create that and do that.
I think it's just to extend the namespace so that you don't use type constructors. They don't steal your names of functions. It's like Haskell is frugal with namespaces.
I see. Okay.
But I told you one thing in the beginning, that all data structures in Haskell or data is immutable. Never changes, right? You cannot mutate any data. So in particular, it means that if you construct something, once you've constructed it, it remains the same forever. So any object has a memory of how it was constructed, right? Because when you have mutation, then the object forgets how it was constructed. Goes away, this information. Whereas in Haskell, every data remembers how it was constructed. And that's extremely important because you can later ask an object or variable, let's say, and you know by variable I mean invariable, how were you constructed? For instance, here we have only one constructor, so this constructor, right? But later we'll see multiple constructors, so you can ask data, how were you constructed? Which constructor was used? And what were the arguments, the values that were used? So like if you construct a pair of 1, 2, you can ask this pair, how were you constructed? Oh, you were constructed using this, you were constructed using this P, and you were passed 1 and 2? Okay.
Bartos, how is it that you know that the same thing cannot be constructed in two different ways?
What do you mean by the same thing?
Like once you have P of AB, how do you know it's not Q also Q AB?
Well, Q of AB will construct a different type. Is that what you mean?
There's only one type constructor for a product?
No.
The product
No,
have two?
no. There can be many others, but they form different types. Their type is distinguished.
So each type has
It's
at most one constructor?
No. But we'll get to it. Okay. Let's not jump. So remember where we were doing this square distance, this awful example that was taking a pair? We can actually do square distance using this implementation of product because a pair is a product, right? So we could say SQ dist. Okay, maybe I should put a prime or 2 primes. In Haskell, you can use actually apostrophes. Yeah, you can use apostrophes in names, which is kind of good because that's how mathematics. So, so suppose that I'm passing a product rather than a pair. It's actually product is the same as a pair, same in the sense that they're equivalent. So suppose that I define square distance to take a product. So I can pattern match it immediately using the constructor. I can say, hey pair, were you constructed using P and let's say X and Y, just not to confuse the names. Okay, and if you passed it a product, then yeah, it always matches this pattern, right? There's just only one pattern for products. Product is always constructed using the P, and you can extract X and Y, and now they have the values that were used in constructing this pair that you are passing to square distance double prime. And then you can say, okay, X squared plus Y squared. Same thing, right? Now what's the type of square dist prime? Okay, the type is, what does it take as an argument? What's the type of the argument? It's this. It's a product
Of num, right?
of num, right? Okay, so I have to be more specific.
So
I
it's
have to say that
Num
num A and
num B.
num B. So both A and B are of the class num, right? And double arrow says if A is of class num and B is of class num, then square dist prime has the type product of AB arrow. Probably I should put num_c here too, right? num_c to c.
Wait, how you
No, wait a moment. It has to be the same num, right?
We just not very.
Well, yeah. Just as num a and product a.
Wait, why don't you ask GHC what the type is?
Yeah, ask
I just
GHC.
did.
Oh, I see. But we figured it out,
I
right?
compared earlier.
Okay, I wasn't looking. So num a, and it takes a product AA and returns A.
The constraint should be the same A because
Plus.
of the type reference on the plus. They have to be the same type.
Yeah. Plus cannot take two different types, right? It has to take both of the same type, unless
How clever!
you have to do conversions. Yeah. Yeah. Because the type signature of plus, I'll show them what the
Why
type
don't we just
signature of
get rid of
plus is.
Bartos and ask GHC?
Yeah.
Yeah, so
No, I will be asking questions and GHC will be answering.
plus constraint is A to A, where A is in num, and then it's also just to know what the exponentiation operator
Okay.
as well, which I think is
Now comparing
integral.
to this.
Integral and num in it.
Yes.
A has to be num, the B has to be some integral type.
Wait, what?
Which is why that step wasn't compiling earlier, because I was trying to do x to the power 2.0. It's not.
Not to be confused with integration, this is just, like an integer.
Right. Yes. Integral contains like integer types.
So I haven't introduced type classes yet, but you see how they work, right? I mean, you have to specify that it's not one particular type, but it's a whole class of types which have a particular property, and one of them being able to multiply them and add them. Right? Okay. So the first argument is product AA.
It's not a property, it's a function. It's a particular function. Plus.
Yeah.
An
It supports a
implementation
part.
Plus.
Some people even call it a method, right?
Method.
Of num. Num has a method plus, and has a method minus, and has a method multiple. Right? Okay, so that's nice. Now the same goes, actually nobody uses this because there is a built-in type of pair, right? Which we could sort of write in this way, okay? Instead of calling it a product, I will call it paren, paren. Okay, that's the name of my type constructor. And the name of my data constructor is the same. So I replaced P with this, and it's fine. So there is really no special construction for pairs. Pairs are just a product type, and with a funny type constructor and a funny data constructor.
Now, before you said we take like this plus over here, we take an operator, we put it in parentheses, and suddenly it's fancy pants. Is this comma an operator that's in parentheses, or is this something
Oh,
different?
yeah.
Okay, so you can use this one, for instance. You can say paren, paren, 1, 2, and you'll get a pair of 1, 2.
But is the comma the function, or is it parentheses comma the function?
Yes.
Yes.
Parentheses are the notation.
It's an infix outfix operator.
The important thing is that there is really no such thing as an operator. Operators are just functions, but there are naming conventions that Haskell uses, and things with punctuation or parentheses. Well, parentheses are used to make infix.
Well, I think that the real answer is this is built in into Haskell.
Yeah.
Yeah, comma is a
I'm just-
special operator that
Right,
works
comma.
differently from, say, plus.
But like, you can't just do
So I don't think that the
3, comma,
compiler
4
would
without
actually.
the parentheses.
Does that mean like a triple is just that, like twice, like a pair, where the first element is a pair?
Oh, that's a little bit more complicated. It is sort of like a triple. You could say it's a pair in which first element is a pair, or you can say it's a pair in which the second element is a pair, right? And they are all equivalent,
There's
but
a
not
natural
equal.
A natural
It's not the same type.
So doesn't that mean then though that the comma float is not really an operator like?
There are some special cases. I mean, the lists and
Yeah.
which we'll get to.
This is built-in types, but it sort of works as if there were operators that are infix, outfix.
Hand your badge in. That's great.
So when we're previously defining square distance using this pattern matching on a pair, we are pattern matching on this, essentially. Now, so pair is like the basic product type that's built into Haskell. And from this you can construct more products. Like as I said here, you can have a triple, and you can build like a pair which whose first element is a pair, and you can call this a triple. They are all equivalent, but they are not the same type. Okay, they're just equivalent. They're isomorphic. Yeah.
Guys, can you tell the people, are we going till 9 or?
Oh.
Can you tell them what the cutoff is?
Okay, let me see. That's actually a good point to stop. Let me just finish with the products.
All right,
No, I won't finish with the products, but I'll tell you one more thing about products. Is that these products actually come under disguises in other languages, and also in Haskell you have sort of built on top of a simple product, you have more complicated products. For instance, it's often not very good to have like a triple. Well, something like this. Let's suppose that you have a function that takes an integer string and a triple, right? And then you have to ask yourself, okay, but what is this one? What if I, change? Maybe this is username and this is password, right? But the type is the same, so the compiler would not complain if I exchange them. So very often when you have more stuff, and they have actual meaning, then you might want to name the components differently, right? And when you have product type that has named components, this is called a record in Haskell, and has some syntax that I'm not going to talk about yet.
I see, and then the names are just the function, the
Yes.
projection.
Projection functions, exactly. So in most languages, you don't have this hand sticking out of water. You just have these fingers, and you don't understand that there is one theory behind all this. All data types are actually either products or sums, and I'll talk about sums next time. Okay, all data types, well, except for the higher order data types, which use functions. But these are called algebraic data types because they use only product and sum. Right? And compare this to type systems of even Java. It's like there's so many different ways of defining data types, and it's not clear that actually it all is just two ways of constructing new types from all types: product and sum. Okay? Thank you.